Thank you very, very much. I'm delighted to be here. Thanks a lot to the organizers for inviting me to speak. I'm, of course, not an expert in the kind of areas that are being discussed here. I suspect I'm here to present this kind of point of view. I gave a similar talk at Cornell a number of years ago, whose title was Three Cheers for Shut Up and Calculate. In the intervening time, my views have changed a little bit. So as you'll see in the very last slide, I'll be giving 2 cheers for Shut Up and Calculate, although if we get there, you'll see really more precisely, it should be square root of 3 cheers for Shut Up and Calculate. Now, this point of view that I want to talk about and give 2 cheers for, square root of 3 cheers for today, is one that, of course, normally is associated with the discussions of interpretations of quantum mechanics, but is maybe more generally the attitude, maybe in modern times most eloquently put forward by the late, great Steve Weinberg, that in our development as theoretical physicists of fundamental physics, it's not especially useful to explicitly think about philosophical considerations in what we're doing. Obviously, this is not to say that philosophy of physics, philosophy of science is uninteresting. It's an absolutely fascinating subject. All scientists, all physicists should know more about it, as well as the history of physics and science more generally. But it's a more sort of specific point that if you don't think more philosophically, you're screwing up, that you're missing an opportunity to make more progress on fundamental physics. And the counter side, the other side, is like, the really great revolutionary discoveries of the 20th century were made by people like Einstein and Heisenberg that were very explicitly philosophical in the way they went about making their great discoveries. And while there's been very impressive advances since then, filling out the standard model of particle physics and our understanding of cosmology, it definitely is true, and that those discoveries were made in a much more pragmatic, much more shut up and calculate flavored way of doing physics. Those discoveries are definitely less revolutionary and less of a big deal than the discoveries of relativity and quantum mechanics, which I absolutely 100% agree with. Those discoveries are really filling in an intellectual framework that was sitting there already from these much, much bigger deals that were handed down to us almost 100 years ago. And today we do find ourselves in a situation where it's likely that the next steps that are needed are similarly revolutionary. So it could be that it's a reasonable argument that we have to switch to this other way of doing things, the same way our great ancestors did when they were confronted with this kind of a question. And that's the more specific point I want to talk about. Why, especially in the current environment that we're in, the shut up and calculate philosophy is the right way to go. Well, at least I'll give it 2 and not 3 cheers. Now, of course, this attitude is sorry, and the title. Oh, sorry, I don't know why this is not. The title of the talk, of course, is an homage to this amazing book by E.M. Forster from 1951, 2 Cheers for Democracy. And E.M. Forster withheld the 3rd cheer because democracy encourages mediocrity. And that is not the reason I'm withholding my 3rd cheer. I actually think shut up and calculate is the best inoculation we have against mediocrity in fundamental physics. But if we talk about the sort of caricature of these 2 points of view, of course, this is an extreme caricature. But the caricature of the shut up and calculate person is the problem set addicted calculational monkey nerd who doesn't care about anything, just, calculating things, agreeing with experiment, moving on, not thinking about what it all means, not thinking anything about what the grand underlying principles and ideas are. And on the other side, the caricature is, but let's just spend all of our time thinking about what quantum mechanics really means and be brave asker of big questions that these monkey nerds are not willing to think about. Okay, that's a caricature. But what I want to do in my remaining 25 minutes is give a more nuanced picture of what the shut up and calculate philosophy is really about. Okay. So from my point of view, shut up and calculate is really equivalent to actions speak louder than words. It's really equivalent to where's the beef in any discussion. And it's a shorthand when people say it. They're not telling people don't think about deep, important questions. It's almost the opposite. It's a shorthand for the distillation of what many of us feel is the most effective strategy we've found to attack and make real progress on the biggest, hardest, and indeed the most conceptual mysteries of physics. And this really has something to do with what we've discovered about the structure of physical laws. And again, I'm not an expert on the description of these things. I can just tell you the way I understand it as a practicing theoretical physicist with my feet on the ground. The structure of physical laws has two parts, obviously. There's some mathematical structure, and that's associated with equations. But the equations are definitely not the whole story. We also have to have a physical interpretation. That means that there has to be a dictionary and a grammar for converting the mathematical equations into statements about the real world. This is why I'm often frustrated when people say, oh, look, we can write this one equation, you know, Einstein's equation or the Lagrangian or the standard model, and that's it. This one equation describes the whole world. Incredible. Yes, but it needs a gigantic dictionary to describe precisely how you take that equation and convert it to statements about the real world. Both of them are necessary. The job of the mathematician is to discover amazing mathematical structures. The job of the theoretical physicist is to find those mathematical structures that have something to do with the real world and find the dictionary and the map between them. So this means that there is a role, obviously there is a role for thinking about what the words mean at the heart of what fundamental physics is about. This fact about the structure of physical laws is also mirrored in what I think of as the central creative tension for the theoretical physicist. Because as you go about doing your work, if you want to do anything of any importance whatsoever, you have to balance these two countervailing forces in your own psyche. On the one hand, you have to be driven by some grand physical or philosophical principles, at least in a rough and ready sort of philosophy for what you think the next set of laws of nature should look like, what ingredients they should have, what their rough shape should be. On the other hand, in order to actually do something when you wake up in the morning every day, you have to find some very insightfully chosen calculations. Or, of course, take inspiration from data, that new data from nature, but we're not in that situation largely today. We're taking a lot of, instead, insight from what you can call theorist data, doing relevant calculations that tell you in an interesting way what to do next. And so this tension is also there in the sort of in the intellectual personalities of theoretical physicists that have to combine these two ways of being. You have to be a romantic dreamer on the one hand and a careful pragmatist on the other, and you will go nowhere if you're only one or only the other. So that's also clear ahead of time. But where there starts to be an asymmetry, when we go back to the structure of physical laws, while both the equations and the words are important, in some invariant sense, the equations are ultimately more important. And the reason they're more important is very simple. While the words are needed for making the dictionary between the equations and things that we see in nature, we've seen time and time again that the words themselves can be imprecise, they can be slippery, they can lead to complacency. Often you find what you think of as the one correct set of words to say about the equations, and it blinds you to other ways of thinking about the equations that lead to totally different paths of progress in the future. And maybe most importantly and most invariantly of all, the words can change radically while the equations are entirely unchanged. And maybe one of the most famous examples is with Maxwell's equations. Famously, Maxwell came up with his equations thinking about a crazy model of a mechanical ether with cogs and gears and wheels. Those of you who have not studied Maxwell's ether should really do so. It's a stupendous construction. I think it's an absolutely amazing thing. But that was his picture of what Maxwell's equations were about. And later we understood better, well, that ether was unnecessary. It's really something about relativistic theories classically. And later we understood that it's ultimately a statement about quantum mechanics and the fact that photons have spin 1. As we went, the words that we wrapped around the equations totally changed, but the equations amazingly stayed literally on the nose exactly the same. Okay, so there was something more correct and ultimately more important about finding the right equations than necessarily finding the right words. And this is related to the comment I just made a second ago. You might wonder, given that the final form of the laws are so simple, here we can write down on the left Einstein's equations, on the right Schrodinger's equation. Surely we can find them. I mean, why do we need all this crazy sit around, do lots of calculations, follow, find theorist data, theoretical data, et cetera? Why not just, surely we can just get to these equations more directly if we have the right philosophical mindset. So what is all this theorist data, shut up and calculate crap? And going back to the tension that I talked about, the grand physical and philosophical principle are absolutely, definitely indispensable. But at least in my experience, they're the easier part. It's easier to come up with grand philosophical prejudices, ideas. I'm going to go that way. Okay, and people can decide to different prejudices of this sort and go off in different directions. The really hard part, the much harder part, is the second part, the insightfully chosen calculations that generate the theorist data, which is where, in my experience, the heart of the action is. And why is this the case? Again, the reason this is the case is not something about sociology of science. The reason this case is not something about sociology of science. I think it reflects something about the structure of the laws themselves. For mysterious reasons that we still don't understand, the laws of nature, the physical laws of nature, are mathematical, they're simple, and they're rigid. And it's the simplicity and the rigidity that makes it especially useful to think more in terms of equations and less in terms of words. It's because they're mathematical and simple and rigid, it's much more forgiving of little errors to guess the correct equations when you're somewhere in the basin of attraction of the right set of ideas. You need to be in the basin of attraction of the right set of ideas, otherwise you're screwed. But once you get there, what gets you to the end is this second process of guessing equations. I actually want to spend a few minutes to talk about these sort of two very famous examples of Einstein and Heisenberg, which are often held up as examples of how thinking more philosophically was crucial for making huge progress. And indeed, for the first part of heading in the right general direction, they're absolutely crucial. But I want to tell you something about at least my reading of the history for why, in Einstein's case, it did almost as much harm as it did good. And why, at least in my reading of what Heisenberg did, I can tell you what I thought he did, and where precisely the more philosophical way of thinking was useful. So, but again, the sort of famous story is that Einstein just had the happiest thought of his life that someone falling off a building didn't feel their weight, the equivalence principle. And the sort of popular story, of course, no professionals know that this is not true, but kids in school learn that was the central giant thing. I don't know, it was 8 years, something happened, blah, 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 and then general relativity. Okay, so, and then Heisenberg says, we should only speak of observables, right? That was the great thing exactly 100 years ago in Helgoland. We should only speak of observables, and boom, that led to matrix mechanics. That was a sort of key insight that got people going with quantum mechanics. So I want to talk about these two examples. And let's start with Einstein and the principle of equivalence. And I'd like to see historians of physics talk about this. I'm sure they have. But I can tell you for a fact, there was no way in hell that you needed Einstein's genius to discover the principle of equivalence. Because I discovered the principle of equivalence in 1986 when I was in high school. When I was in high school, I liked, and I'm not Einstein. When I was in high school, I loved nothing more than solving classical mechanics problems all day long. A few years later, people told me about Lagrangians, and I was devastated that you didn't need to do all these force body diagrams. All I like to do all day long is solve classical mechanics problems. And in hindsight, a mean older friend of mine gave me the following problem. He said, look at a triangular block with a ball and a spring attached to the bottom and accelerate the tip of the triangular block with an acceleration a. What is the equilibrium position of the block? And I'm like, great, thank you very much for another problem. This one doesn't involve shooting monkeys, so it's a little more kind. So I worked and I worked and I worked and I worked and I worked, and I find this final answer, which was the tangent of the angle is the a acceleration over g. I'm like, holy crap, that's exactly as if the gravity was really pointing in this direction. Oh my God, the acceleration is just like there's gravity pointing the other way, right? That's the principle of equivalence at the level that we credit Einstein for. I would be absolutely shocked if this principle was not understood by people hundreds of years before Einstein. The deal is not the principle of equivalence. The deal is what to do with it afterwards. That's the hard part, okay? Because it's entirely non-trivial how to take this idea that a kid in high school could have and turn it into Einstein's equations. And it is not just a matter of following this up. There's several significant new conceptual insights needed in order to do that. Now let's think about Einstein's own history. So these are some pages from the Zurich notebook. There's a story, again, I'm sure all professionals know, but Einstein actually had the Einstein equations way before 1915. He had them in 1912. They're written down in his Zurich notebooks. And reading through his Zurich notebooks is an amazingly inspiring thing. It's not like looking at Newton's notes for the Principia, which is like Mozart. You know, Newton wakes up in the morning and say, today I will calculate the square root of 2 to 20 decimal places because I can. You know, so Newton, everything was perfect, everything was right. Einstein was more like Beethoven. Einstein is screwing up all the time. Okay, so when you look at his notes, you see he has pages and pages messing around with the Christoffel symbol, discovering the metric, making all kinds of mistakes, practicing, raising and lowering indices, all the things that students of general relativity struggle with. Einstein struggled with even more mightily in coming up with GR. Okay, so anyway, it's very inspiring. Looking at these things, a sort of curved space-time metric makes an appearance very dramatically on one page. He practices with indices. The notion of curved space-time and motion in curved space for him begins with a practice problem of seeing what happens for the motion of a ball on a sphere, not in space-time, but just in curved space. Okay, but then and then later the Riemann tensor appears, the Einstein equations appears. He is terrified of the Riemann tensor. He writes here in German, this is too involved, okay? On this page, he almost has the Einstein equations exactly as we have them in their current form today, and he abandoned all of it, okay? He abandoned all of it in 1912 to set off to work with his friend, Marcel Grossmann, and they came up with this infamous Entwerf theory, okay? The Entwerf theory is a huge and confusing mistake in the development of general relativity. But it's important to say that just as philosophy guided Einstein towards getting to this set of ideas, it was also used by him repeatedly in justifying this huge and confusing mistake. He used Mach's principle, he used physical arguments like the famous Hole argument, all these things that ended up being totally wrong. He confidently declared every 3 months in his letters to his friend, this is the right thing, okay? And he justified it by exactly the same kind of philosophical prejudices that, again, got him into the right basis of attraction ideas to begin with. Okay, so ultimately, he had to abandon those ideas. Anyway, we won't talk about the history of general relativity, but this entire detour was as justified in Einstein's own mind as the sort of philosophy that got him into doing this kind of thing to begin with. Now let's talk about Heisenberg's journey. This is, to me, even more interesting, because Heisenberg and all of his young friends were struggling to extend Bohr's model for the hydrogen atom to helium and other realistic systems. Okay? And as usual, helium is a very hard problem, so they decided to work on toy problems. So the toy problem they decided to work with is the n-harmonic oscillator. Okay, so this is so just not just harmonic oscillations, but with a little nonlinear correction to the classical equations of motion. Now, any undergraduate physicist knows that to solve this problem, since the leading order, you're just bouncing back and forth at some fixed frequency, it's useful to expand things in Fourier modes. So it's useful to go to a Fourier space, expand the answer as a sum over motions with many different frequencies. And so beginning with this, with the variable x of t, it's very natural to switch to the variable xn. And if you look at what x squared of t is, again, this is something every undergraduate in Germany knew at the time, and everywhere else in the world. Well, there's a formula for it. The x squared nth component has a formula that looks like this: the sum of xm times the sum of xn minus m. Okay, so it has that simple character. But now comes the magic. Heisenberg says in his paper that, look, it's funny that when you look at the actual observation, what you see in an atom is a transition between two levels. Okay? So what we actually see is not one level or the other level. It's not labeled just by an N and an M. What you observe is something that's labeled by two indices, N and M, which is omega N minus omega M. That's just the energy difference, the frequency difference between the first level and the second level. And that's what he took some inspiration from. He said, look, you have this omega that's labeled by two integers, not one, N and M, but the x's are only labeled by one integer, N. That's funny. Shouldn't we have it so that the x's are also labeled by two integers, N and M? Okay? That's it. That's a guess. That's the leap. That's what he did. I can tell you that, if I was in the basin of attraction of these ideas, I would have tried something like this too. This is a classic example of screwing around, okay, to see what happens. And what he did, well, this is really what is the English translation of his paper. He follows those rules. He discovers that x times y is not equal to y times x in the quantum theory. He discovers all sorts of other remarkable things. But what I want to emphasize here is it's a precision of equations that brings some deep truths out of the real dark. In this case, Heisenberg was absolutely in the dark. Everyone was in the dark. It's the rigidity of the equations that makes guessing and analogizing very powerful, much more powerful than you could get just with words. There's something about this paper I think people don't know. People say that Heisenberg used these ideas to solve the harmonic oscillator and so on, but he actually really stuck with this n-harmonic oscillator, and he did a very hard calculation to figure out what the corrections to the energy levels were up to second order in the expansion of this small n-harmonicity. And so he had to do some hard calculations to get these crazy numbers, 51/2, 59/2, and so on. But he did this calculation and he compared with other methods that Bourne and others had come up with, found perfect agreement. And he says that the fact that one obtains exactly the same result seems to me to furnish remarkable support for the quantum mechanical equation that have been here taken as a basis. So even at the very birth of quantum mechanics, some non-trivial calculation was done that works non-trivially, not just some numbers like 1 and 2 matching, but crazy things like 59/2 matching. And when the equations work magically and non-trivially, you're on the right track. Okay, so let's go back and ask again, why so much torture? In both of these examples, why so much torture when the answer is so simple? And I think this is because over and over again, in the trenches of discovery, it is crucial not only to find both why what is right, but again, that's the much easier part. It's crucial to know why everything else is wrong. And this ability to delineate between right and wrong when you're extremely confused about what's going on, the main guide we have for doing this are the equations. So the words in philosophy are especially useless for this last part. Okay, because even when you're right, as we said, even when you're absolutely right, even when the equations are absolutely right, the words can change. The interpretation can change, but it's the equations and calculations that are sure things in totally uncharted territory. Okay, so I want to close with a couple of examples from the most famous aspect of this shut up and calculate philosophy debate, whatever you want to call it. Related to interpretations of quantum mechanics. Now, I think most of us in physics think that quantum mechanics is the most mind-blowing discovery of humanity. It's way too big a leap to make in some methodical or careful way. You need to see the magic. And I showed you how Heisenberg saw magic in the very, very first paper. The correct equations in the case of quantum mechanics definitely came worse. The correct words came much later, and some people aren't entirely sure if the correct words exist today. Okay, but certainly the beginning of the correct words came much, much after the correct equations. But the fact that it was possible to come up with the correct equations to begin with is, I think, a real triumph for the shut up and calculate approach and a template for attacking similarly huge questions we have today. Now, I don't want to. I want to just declare what the non-trivial thing is about quantum mechanics. Okay, so I think we all know that what the crazy thing about quantum mechanics is it changed what it means to know something compared to classical physics. Okay, and it necessitates the following thing that I think the founders of quantum mechanics understood very well, and Bohr was such a crappy explainer of things that he managed to turn it into a terrible fog. But I think the other people around him understood it, in my view, very, very well. So quantum mechanics needs the following thing. It needs you to imagine that you're carrying around infinitely, you have to make infinitely many measurements because the world is probabilistic. And importantly, you also have to do the experiment with infinitely large measuring apparatuses in order to have something exactly classical that makes a classical record of measurement outcomes. When these infinities are present, at least in principle are present, of course they're never present in practice, but when the infinities are in principle present, then there's no, at least in principle, difficulty with applying quantum mechanics to describe the world. We can talk about what it means, blah, 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 but there's no, in principle, difficulty with applying quantum mechanics to describe the world. And the problem is that there are actually situations where this sort of foundational fact about quantum mechanics actually has teeth in telling us something about the limitations in that are imposed on us in trying to describe the world in quantum mechanical language. And these occur when the words gravity and cosmology enter the scene. If you don't have gravity and cosmology, there's no difficulty with making infinitely many measurements with infinitely big measuring apparatuses. But gravity really does not like this division of the world into an infinite part that does a looking at and a finite part that's being looked at, because everything gravitates. That's one issue. And various questions, both in physics of black holes as well as in cosmology, give you fundamental, in principle, limitations on the number of times you can repeat the experiment. That makes it impossible to carry out the experiment infinitely many times in a meaningful way. Both of these things are places where this sort of foundational fact about quantum mechanics really, really matters. It matters for figuring out how to talk about gravity in a quantum mechanical way, what the observables are, and so on. But I find it interesting that even though this foundational fact about quantum mechanics has been appreciated for a long, long time, and these qualitative facts about the way gravity and cosmology change the story have also been appreciated for a long time, the people who have made progress on figuring out what these teeth actually mean have been the shut up and calculate people. Okay? And I'll give you two examples of that. One of them is actually involves Alan, who's sitting right there. I think it's actually the simpler of the two examples. But one of the examples involves what you can call the wave function of the universe. And this spectacular picture of how tiny quantum mechanical fluctuations that are present in the vacuum, if there's inflation, an era of exponential expansion, inflation in the early universe, are stretched out to turn into hotter and colder spots on the sky that ultimately collapse under their own gravitational weight, giving all the structure we see around us. It's an absolutely spectacular story, but it most certainly involves applying quantum mechanics to the entire universe. And it opens up some kind of interpretational questions. Are we doing the experiment over and over again? There's just one universe, right? So what does it mean? How am I supposed to interpret what this wave function of the universe means when I can't do the experiment over and over again? That's sort of textbook quantum mechanics. Well, the answer ended up being that the universe itself, making some assumptions like a translational invariance, the universe itself does the experiment over and over again in different parts of the sky. And instead of averaging over trials, you just have to average over space in the sky. Okay? Now, this is a relatively simple point, but it's definitely something novel in thinking about how you apply quantum mechanics to observations. It was not stated in this language before. And I wasn't around when Alan and friends were understanding this, but this explicit point came up maybe later in discussions. But the first thing that happened was that the calculations were done, you got an answer that made sense, and then you back interpreted the way to correctly think about it. It was certainly not people abstractly wondering about what measurement means that told us that, there's this interesting situation where it doesn't have to be do the experiment over and over again. It could be done, the experiment is done by the universe in different spots and you have to average. That works because of the physics of inflation. That works because the whole point is that we get approximately exactly the same physics in enough different regions that we can average over them. It's not something you can sort of just think about abstractly. It's something you have to see in an example and see how it works. That's the first example. A second example, maybe a deeper example and a more recent example, has to do with maybe the most fundamental obstruction that gravity brings into the game when you talk about quantum mechanics, which is that there are no local observables. So that's a fancy way of saying the following. If you want to imagine talking about anything to arbitrary accuracy, and we imagine in physics that we have mathematical theories that make predictions for things that it can, in principle, be talked about to arbitrary accuracy, measured to arbitrary accuracy. But in a world without gravity, there's no difficulty doing that. You just make your apparatus bigger and bigger. You do the experiment more and more often. And the answer that you get converges better and better to the predictions that you get from a quantum mechanical theory. But with gravity, you can't do that. With gravity, you can't do that. You can't make any arbitrarily big apparatuses in a fixed size room, in this room, because as you make the apparatus bigger and bigger, it gets heavier and heavier. And before it can get arbitrarily big, it gets so massive that it collapses the room into a black hole. And you're screwed because you're inside the black hole and you have a finite amount of time to do the experiment because you're crunched in the singularity. So both of the infinities that we need to talk about things precisely in quantum mechanics are removed because of the presence of gravity. This is a remarkable fact. What does it tell us? It tells us that if we insist on talking about quantum mechanical observables in a world that has gravity, the only thing we can do is talk about a tiny subset of all possible observables where the experiments start and end infinitely far away. So we have to assume that the space-time has some asymptotic regions. And then we're not doing it in a fixed size room, but then we can take our apparatuses, move them out to infinity, make them bigger and bigger, repeat the experiment infinitely often. And those are the kinds of observations that in principle have exact meaning when you have quantum mechanics and gravity. In flat space-time, something that's not exactly ours, because our space-time is cosmological, but it's not so far from flat space-time, these happen to be, happily, practical observables that experimentalists like measuring, colliding particles from more or less infinity. At the Large Hadron Collider, it's 27 kilometers around. The proton is 10 to the minus 14 centimeters big. 27 kilometers is more or less infinity compared to 10 to the minus 14 centimeters. So you send the particles in from infinity, they bang into each other, and they go back out to infinity. These are the kind of things we're allowed to talk about, not detailed histories of what happened in the interior of the space-time and so on. That's not something that we're allowed to talk about. Now, this is a crucial insight that physicists like Bryce DeWitt and Roger Penrose had in the 1960s. And this idea that you should only talk about something like scattering amplitudes was a central focus of early work in string theory. In the late 1990s, this philosophy, it was realized, could be understood in a much more practical way in a somewhat simpler system, a toy model of a universe, which is like inside a box. This is a sort of closest thing that we can come up with in physics to a universe in a box. It's a tin can where the geometry on the inside of this tin can is curved, is called it's a hyperbolic space or anti-de Sitter space. In this case, again, this is not our universe, but it's a cousin world where exactly the same philosophy holds. The only observables you're allowed to talk about are associated with things that you can measure at infinity. But here, those things you can measure at infinity turn out to be, you see, if you have this realization, those are the only things that you can talk about, then it's natural to wonder, if those are the only things that you can talk about, why do I need to have an interior of this space at all? Why can't I just have a theory that lives on the boundaries of this tin can where the observations start and end, and just have a theory that just lives there, that gives me the results of all the experiments that I could do anyway? that turns out to be the case. It is possible to do that. That's sort of famous holographic correspondence between theories that have gravity in empty de Sitter space and theories that just live on the boundary that don't have any gravity. It's a sort of shocking thing when you first run into it. It's our first example of what the emergence of space from no space might actually look like. It tells us, among other things, that string theory and particle physics are intimately connected to each other. But how was this discovery made? Again, the basic discovery in the end is super simple and conceptual, but nobody made it directly like that. The path to making this discovery was a long and tortured one. We went from particles to strings to discovery of all kinds of other objects other than strings that lived in this theory. People naturally ask what happened when you put these objects on top of each other. They found when you put them on top of each other that there was some geometry, kind of like a black hole, that's produced by the presence of all these objects on top of each other that looked like this empty de Sitter space that no one was paying much attention to beforehand. Then there were natural questions like what happens if you throw something in from the outside and it bangs into this collection of objects and things come back out. And gradually those calculations looked exactly the same as calculations that did not involve the interior of a space at all. So long and sort of tortured path of this sort to get to something where by the time you get to the very end, you can delete all of this history and just say the right answer at the end. But there's a good reason no one came up with it that way. There's no sort of continuous way to make a leap like that, but you can make such a leap by taking several steps that roughly go in the right direction. Okay, and there's a lot yet to do. Our universe is accelerating. This has many implications, but maybe the most profound one is that what we see out there in the universe is what we're ever going to see. So there's a sort of fundamental finiteness that's thrust on us. Everything outside our cosmological horizon is accelerating away from us. Light from it will never get to us. In a fundamental sense, this is the first time in physics that finiteness has been absolutely thrust upon us. There's no way to get an infinity. And that means that we can't talk in any precise way about quantum mechanical observables. This is the first place the rules of quantum mechanics cry uncle. This likely needs not just the emergence of space, as we've understood for the past 25 years, but the emergence of time as well from more primitive building blocks. In my view, it very likely needs an extension of quantum mechanics. These absolutely go back to the same foundational facts about what it means to know something in quantum mechanics, but now really on steroids. And my own view is that while we've seen for the past 25 years how space can emerge from quantum mechanics, that what we're ultimately after is something quite a bit more radical. Some other set of ideas, I don't know what they are, some question mark, but from which quantum mechanics and not just space, but space and time will emerge together, joined inexorably. Much of my research over the past 10 or 15 years has been motivated by trying to attack this question. But again, in this way of proceeding, by looking for clues in magic under our noses, trying to find some way of thinking about ordinary physics that does not put in space-time and quantum mechanics, but gets the results out that we normally think space-time and quantum mechanics are crucial for. So, there's a lot of room for new revolutionary thoughts, but my own sense is that we're going to have to get there in this more gradual way. All right, so let me just end. I had a few more things to say, but maybe we can have some discussions afterwards as well. The obvious question that one gets is, but don't you really care about what reality really is? Not just a bunch of abstract equations that describe it. That's a great question, and my answer is I 100% care about what reality really is. I care about it so much that I don't want to screw around finding out. And I think what we've seen is that whatever reality is, it has time and again proven to be vastly different than our preconceptions. And I care too much about this question to overly pollute things with my own prejudice-laden words and thoughts. Even in very small examples, I've seen how my words and thoughts make me go the wrong way. It's very easy to go the wrong way, at least for me. Maybe other people find it easier. I prefer instead to try to listen. So the point of shutting up is not to shut other people up. It's to shut yourself up. Okay? You want to shut up and listen to what the world is trying to tell you to do next. I listen by calculating. So that's what shut up and calculate means to me. But why the 3-2 cheers? So let me just end with this. So so there is a danger here. And I think the spirit of shut up and calculate is that you just sort of follow your nose and do what comes next naturally. Theoretical physics is a huge structure, glorious structure, so many hints about what to do next. So you just follow your nose, do what that. Don't worry too much about what it all means. Follow your nose and do what comes next. And I think that kind of gives you a picture of a random walk. Okay, so sometimes you go the right way, sometimes you go the wrong way. Individuals do, the whole community does. But when there is a kind of wind, the wind of data, either data from the real world or some kind of self-imposed wind, it's some sort of conceptual clarity of the kind of thing you want to see, the sort of direction you want to head in, that's less good than the real world data, but it's still something. The wind means that you're not just random walking. You are random walking, but the drift is in some positive direction, okay? So that means that the progress is linear in time that you spend on it. Now, what can happen if this data is not there and you're not guided by some kind of conceptual clarity about what it is you're trying to accomplish, what the big picture goal is all the time, and how precisely what you're doing is related to the larger philosophical ideas or physical ideas you're trying to realize. If all you're doing is pushing the next frontier of the cool things that you've understood in theoretical physics, then the danger is obvious. There's still progress, but it really is a random walk, and the progress grows like the square root of time. Okay? I think we'd all prefer to have progress that's linear in time than square root of time. And I think this is thinking more about this, thinking more about precisely how and more effectively we can use principles and philosophy to guide what we do, not just individually, but a little bit more collectively going forward is, I think, a useful thing to think about. So thank you very much, and sorry for going over time.
We'll get into it. Look, honestly, I agree with almost everything Nima says, but my job as the commentator is to provide a slightly different perspective, and therefore I'm cheering for different things. I'm going to cheer for the noisy philosophizing rather than for the shutting up and calculating. And I think that, again, we're probably not going to disagree here. Both have a role. I think that there's lots of different ingredients that come in to thinking carefully about the universe. So I'm going to emphasize the noisy philosophizing, but of course you also need to shut up and calculate at other times. And at other times, maybe most of the time, you need to collect some data. You got to go out and do some experiments. As a little bit of evidence for the efficacy of noisy philosophizing, here's my casual plot of where different famous physicists have fallen on the noisy versus quiet axis. And I think that many physicists have been very good calculators. Every good physicist does a lot of calculation. Very few of them shut up. I mean, maybe shutting up to yourself, that makes sense. I agree with that. But all of the famous names you can find texts in their oeuvre where they're profoundly declaiming on what physics is and what nature is and what our methodology should be. I don't think that's a mistake. Even with Heisenberg and Einstein, we're absolutely true that the calculations they did were crucial to them inventing their great discoveries. I don't think you can really think that it's unrelated to the fact that these two could not shut up about the fundamental nature of physics and reality. Heisenberg literally wrote a book called Physics and Philosophy. Then, of course, there's Niels Bohr, who takes it up to 11. He's off the scale. I put Nima around here, but also notice that, one drifts to the left as one ages, so there's still time. As Nima points out, when you don't know what to do, it is very often useful to calculate things. I completely agree with that. It is a reality check. It helps ground you in what he very accurately calls a theorist version of data. But it kind of is obvious, I think, trivially obvious, that sometimes you don't know what to calculate. And it can be true that thinking deeply and really trying to decide, should I go in this direction or that direction, might involve something along the lines of noisy philosophizing. To me, even more importantly, sometimes you can and do perform a calculation and you think you're proud of yourself for getting the right answer, but you haven't actually understood it. Ludwig Boltzmann, an absolute hero of mine and someone who did a lot of foundational stuff, famously proved a theorem, the H theorem, in the 1870s, which he thought was basically the second law of thermodynamics proven by mechanistic principles. That's not exactly right. There were like crucial details in there that you could get to by thinking harder about it, and indeed there's a lot of controversy about it at the time. I think if you dig into the history of it, I would claim that by the 1890s, Boltzmann was very close to inventing the Big Bang Theory. He could have suggested that the universe began a finite time ago in a low entropy state. He didn't do it because he was calculating things and didn't take quite enough time, even though he was also someone who was happy to yammer on about fundamental principles. I think that thinking with philosophical rigor can protect us from saying, it's good enough as it is right now. Physicists are very good and famous for getting the right answers for the wrong reasons. And that's fine as long as you're really, really sure that your answers are the right answers. When you extend beyond what you know to the unknown, especially in things like cosmology or quantum gravity, making sure that your original reasons are the right ones might be a very helpful thing. I gotta just list specific examples of places where I think this kind of noisy philosophizing is especially appropriate because calculating might just not be enough. I'm one. I think that Nima and I actually do disagree on this. I think that understanding the fundamental ontology of quantum theory is not something that we do, but it's something that we need to do, and some thought is very appropriate there. And one of the reasons why simply calculating is not enough for this specific question is because you can think, well, all right, I have an explanation for what the fundamental ontology of quantum mechanics is, but that raises new questions that you don't have the answer to, and taking those new questions seriously leads you back to the noisy philosophizing. What is naturalness in a physical theory? We spent $10 billion building a Large Hadron Collider. We'll tell you is because we want to discover the Higgs boson, but really, we thought that the value of the Higgs mass was unnatural, and we wanted to find the new physics that would explain it. We failed. We have two very big examples in the case of the Higgs and the cosmological constant where our notions of what is natural and what is not are failing us right now. I think a little bit of thinking about this is called for. What might have happened at the Big Bang? Calculating is going to be very helpful in figuring out what did happen at the Big Bang, but we know so little about this that the space of possibilities is amenable to some careful philosophizing about it. Why do initial conditions have low entropy? Is time emergent? And if so, how? I think this emergent time thing is especially something where people have been talking about it since maybe the 60s. There have been a certain amount of calculations done, but we are hamstrung by the fact that we know the answer. We know what time is. We know how to measure it using clocks. So we sort of look at our quantum mechanical equations and say, yep, there it is. I see time emerging. I am wholly unconvinced by most of what people have done to get time to emerge from timeless quantum mechanics. And I think that this is a prime area where good philosophy of physics could help. There's likewise, I would say exactly the same thing about the anthropic principle and the multiverse. Physicists, bless their hearts, because some of my best friends are physicists, do a very bad job at reasoning carefully and rigorously about what to predict if you think you find you live in a multiverse. Causality, purpose, meaning, and life are supposed to depend on fundamental physics, but I would like to know the connections more. And I'm ambiguous about this one, but maybe we're allowed to ask why the universe exists, why space and time and causality and locality exist the way they do. Here, Nima might have a point. I'm not sure whether thinking about these questions lead to progress or not, but I'm open to the possibility. I want to see a rich ecosystem where some of that gets done. I'll give you one worked example, which actually Nima suggested to me in personal communication a while ago. The holographic principle, as Nima mentioned, is one of these ideas which we think has a grounding, but is still a little speculative right now. It basically says in a theory with gravity, if you have a region of space, the information you need to say what happens in that region isn't proportional to the size of the region, to the volume. It's not spread equally through space. You can encode it on the boundary, like a hologram. And that's an amazing idea. And Nima said to me with perfect justification, he said, look, if these people doing foundations of quantum mechanics were any good, they would have invented the holographic principle. It took Juan Maldacena, doing calculations about stacking brains near a horizon to actually get it done. But it was Adam Becker who pointed out to me, really, the holographic principle first came out of work by Gerard et Tufte. In this famous paper, Dimensional Reduction in Quantum Gravity, he was inspired. He had some wacky ideas about cellular automata and discrete physics and things like that. This is so small on my own screen, I can't read it. But it came out of him thinking about the foundations of quantum mechanics and how they would be affected by the existence of gravity. He has this classic physicist line. One of my starting points has been that quantum mechanics itself is not all that much of a mystery to me. This is something that most physicists think about themselves. It's just that they disagree with each other about what quantum mechanics says, so they can't all be right. I mean, they can be right that it's not a mystery. They can't be right that they're all correct about it. But if you read this paper, which is really the first statement of the holographic principle, there are calculations in there. No one remembers them. They're all about, discrete lattice models, et cetera, et cetera. It's the words that actually came out of here. Had we put more work at this time into thinking about this, we might have discovered Maldasena's duality even sooner. So I'm going to absolutely concede what I think is driving a lot of Nima's point, that there's a huge problem with noisy philosophizing as a way to make progress, which is that there are too few constraints, too few reality checks. You can just spiral off into nowhere by talking to yourself and thinking deeply about the nature of everything. Whereas doing a calculation, you're right or wrong. Doing an experiment, you get the data, and that tells you what you're right. Philosophers, bless their hearts, have been talking for 2,500 years about some of the same issues and haven't decided what the right answers are yet. So what do you do about that? How do you get the right answer? I think the answer is to be noisy, to talk to each other. In specific, having scientists in general and philosophers actually talk to each other about what they think. I think it's even fair to say that philosophers of physics spend too much time worrying about theories that professional physicists don't give a lot of credence to. The answer is to talk to each other. We're doing that here at this symposium. Glad to see it all happen. Thank you very much.